So welcome to today's training on Midas Gen. This is the first of a series over our structural program. And we're going to start off with a basic model, which will be a steel plant structure as we see here on the image. And so these are the dimensions of the plant structure we're going to be working on. We're going to be working in the units kilometers, and the dimensions are about 10 meters high at its peak. The front face is about 20 meters wide, and it's about 35 meters long. And we see that we have a separation of the columns every 5 meters. We have about 4 different kinds of sections: the bracings in blue, the columns in white, and then we have some top beams and some mid beams. So we'll be going through all the process, all the steps on how to analyze this kind of structure, how to design the structure, and in the end, even how to get like a detail report, detail section for some of these metal parts. So we'll be working with steel. We'll be using the A36 from ATM09 standard code. And we'll have, as I mentioned, 4 sections for I-beams or for I-sections, and the bracings will be L. And we'll be selecting them from our database, from our literally a drop-down menu. And we'll just go through, and the program allows you to select, or you can actually also user-define. So from here on out, I'm actually just going to be working on the program itself. So I'm going to open up the program from scratch, and we'll just be working out of that for the remainder of the session. So here is Midas Gen, our structural engineering software. Mostly for buildings, we have another software specific for bridges. This is like a general structure building software. Just a quick, I guess, overview of the commands. It's a ribbon menu, which, as we see, it's similar to the concept of AutoCAD. You have tabs, and all the commands are by icon, not like a drop-down menu like you would see on Windows. And it follows a logical sequence from left to right as you're progressing on the model. Like you start defining your sections, your elements, then you apply your boundary conditions and your loads, then you run analysis, so on and so forth. We have the work stream, which has like the grouping of everything we will be working on, all the sections, geometries, materials, all that. We'll see, some of this as it's going along, how it's grouped. And then another quick note, our units can be changed at any point down here. So for now, we can get started. We're gonna start by defining the materials and the sections. So we'll go to properties. We'll define first material. And we're gonna add. And as we covered in the PPT, we'll just select this code, and we'll select from the database this steel, A36. And so this will be filled in for us automatically based from the selection. We see that this program can actually do other materials like concrete or steel reinforced concrete. We also have norms and sections for that. Or lastly, the user can just directly input whatever material parameters they want to use themselves. So today's focus is on steel. So we'll just select this material. Once we have the section the material defined, we can go to the next tab, which is the sections. And here is again where we're going to add our 4 sections from the database. So we see here too, we have many different kinds of sections you can select, and each section has its own database that allows you to define or to select by design norms. So in this case, we'll use the AISC10, but we can also manually allow the user just define, here's the guideline of these sections. You can also change the offset for some of these sections, or like I mentioned, directly input them by table format. And we have all kinds of sections that you can also define. So even the steel reinforced concrete, combined sections. It's a very complete database in that respect, even composite. So let's get our 4 sections in. So we're going to select them from the database, and we'll look them up by basically by section name. So the first one is the column, and as it's shown in our PDF for the tutorial, the first one is HP 360 by 108. Oh, sorry, this should be SI. Okay, so this is our first one, and we can include in front of this column just to make it a little easier to track. Apply so that it appears here. And then we go to the next one, which would be the top beam. And this is W250 by 167. So we just scroll down until we find that. And again, it shows you here the dimensions. So this is the top beam. Then we go on to the next one, which would be 250 by 89, W250 by 89, which is here. This would be our side beams or mid beams. And lastly, we want to define the bracings, but I'm going to change the type of section to angle. And this would be an L 102 by 102 by 11. So 102 by 102 here by 11.1. And this is the brace. And for now, I can actually click OK so that it can close both windows. So now we have our material and our sections defined. And if we happen to be working with, let's say, wall or slabs or plate elements, then we would additionally define the thickness for something like that kind of element. But in this case, because we're only working on steel, we don't need to do that anymore. So now we can proceed to start generating the structure itself. Midas Gen has a grid system that we can activate or deactivate here, and it can either be a grid by line or grid by point. We see now that my cursor turns on, and maybe it's a little hard to spot through the, I guess, video transmission, but there's a series of dots on in this case, the XY plane that guides me, that can let me draw clicking on that. But in order to make it for this tutorial dimensions, I'm actually gonna have to change the grid a little bit. So I'm gonna go here to structure, grids. And first I wanna define the size of the grid, basically the spacing in between each point. So I want it to be every half a meter. So I just tell it that the spacing is gonna be 0.5, 0.5. And what I also wanna change is the face or the plane of this grid. Right now, if I'm in the 3D view, we see that it's actually in the XY plane face. So I actually want to work for now on what would be the YZ plane. And we see now that this has changed from the 3D view, and just to make it easier, I'm going to do the right view. down here. So now I'm looking at it directly face first or front face, this being local to the plane itself. So it's just letting me know more or less where I am. So now that we're in the, like I mentioned, in the YC plane, we can actually start creating our structure, start drawing our structure based on these grids. So I'm going to go to Element, Create. We see here we have different element types. We're going to be working mostly beams, general beams. Here we select the material, there's only one, and here we select the section. So in this case, we're going to start with the columns. And I'm just going to go here to nodal connectivity. So I could technically work this through just coordinates, just giving coordinate system, but I can also directly draw, and there's a grid down here that guides me on my location. So I'm going to start at the origin for the first point, which is the bottom of the column. And you see now it's telling me the distance as I move it around. So in this case, I want the first column to be at 8.5 meters. And then I'm going to move to the right 5 meters. Click, and then I'm going to go up 9.5 meters. Now on the same line, I'm going to go another 5 meters to when I reach the coordinate 10. And I'm going to go up another 9.5 meters. And then lastly, I'm going to go 5 more to the global coordinate 0, 15, 0. And I'm going to go up 8.5 meters. So I had to scroll out to zoom out a little bit. So there we have, from the 3D view, the 4 initial front columns. What I want to do now is I want to start drawing some of these beams that connect. So all I have to do here now is select a different section from my section list. I'm going to select the top beam. And actually, I'm just going to connect points to points. And what I want to carefully do as well, if I hold down to my scroll button with my mouse, I can move it around on the same plane. I'm going to look for the point that's right in between these two, which the distance would be 7.5, and the height of what would be the 10 meters. And I'm going to draw a top beam connecting to either side. So that now again, now I have my front section with the columns and the top beams, and I'm going to continue drawing what would be now the mid beams. And for that, what I want to do is I want to look for the coordinate at 4 meters high, and then draw across. I don't want it to be completely horizontal. I actually want it to be about half a meter higher, and do the same for the other side. So now I have my columns, my top beams, and my side beams. And what I want to lastly do is draw some bracings that crisscross the, I guess, either side of this. So for that, actually, the bracing itself is I'm going to use it as a different type of element. I'm going to change it to truss. The section will be brace. And note that I am deactivating this option called intersect. What that does is, as I'm connecting these two corners, because they're in the same plane, these trusses or these braces actually cross each other. And so if this option was on, there would be a new node generated there at that connection, but I don't want that for these braces. So I'm just connecting corners. And now I have the complete front face of my plant. I can actually modify this a little bit just to make it a little easier to see. So I'm going to go here to display option. go to the option draw and tell it that just give it a random color to the sections. Each section will get a new different color. So now we see it's a little easier to spot the difference between them. It's a little easier to follow. So now we can continue making our structure. What we're going to start doing now is just a series of copying certain sections into different directions to generate the structure that's, in the sense, almost symmetrical. What I want to do, though, is actually change my plane, my work plane again, go back to the XY plane. So now we see this has changed as well, this coordinate system. And what I want to do is I want to copy some of these columns and top beams into the plane in this direction. So we're going to go to translate. It'll be into the X direction. Translate, I'm going to carefully select the outer columns and the 4 top beams. And here I can tell it in which direction and how many times. So I'm going to tell it 5 meters in the X direction, and I want to do this 7 times. You know, if I go to the isometric view, we've seen what we've done. We've basically copied into the X plane. We no longer really need the grid anymore for drawing, so I'm going to deactivate it. So now we have a general outlay of our structure. And what I want to do is I want to connect all of these. So I'm going to go back to create elements. And actually, all of these commands can also be selected here. So I'm going to create elements. This element type is beam. It's the top beam. And I want this option to be on, since what I'm going to do is I'm just going to draw a line all the way across connecting the first to the last columns with the section top beam. But the program is automatically creating and connecting nodes at the intersections. So this is why this is important to turn on in this point. So I'm going to do the same for all the, I'm going to basically make a grid out of the roof by just doing this all the way across. So I can rotate my model by holding down Control and the scroll button to make it a little easier to connect these other sections. And the program actually also automatically locks onto the mid of any element, so that makes it easy for me to create an additional 2 rows of these top beams. So we see if I keep rotating it, it's now a complete grid of top beams connecting all the columns and the top beams to themselves. So what I want to do the next is then do something very similar, but just for the side beams. So just change the type of section that I'm using and do one for this side, and then rotate the model and do the same for this side. And then go back to the isometric view. So now we have some side nodes, or some side beams, some top roof beams. And what I want to do is basically now copy this from face across to the other end. So again, I'll just switch my command to translate. What I want to select, I'm going to do the front view just to make it a little easier to select, is I want to select the internal elements, but leave out the ones that we had already copied, which were the roof and the outer columns. And I'm going to tell it that I want to do this 1 time a distance of the whole structure, which is 35 meters. So 1 time 35 meters. And we see now we've copied the other face. So the structure is starting to come together. And the last thing we need to do is start to draw some additional bracings. If you recall from the initial image, we had a lot of bracings for our structure. So we'll start with the bracings on the roof. So to make it a little easier, I'm actually going to isolate only the roof for a moment. So I can go to here to my works tree, expand by type of section or property. If I go to the Works tab, And I can actually even do something like select the top beam section and tell it that I only want to activate this section at the moment. And then I can go to top view, and now it's much easier for me to find the nodes that I want to connect for the bracings. So I can now go back to create elements. I'm going to select again truss because I'm using the bracing section brace. And again, because I'm working with the bracings, I want to deactivate this intersect option since they cross each other in the center, and I don't want additional nodes created there. So I'm going to do just literally connecting dots, and it doesn't really matter the sequence. I can go all the way down and then just come back up. But I'm only going to do the bracings for the left side, the very first row, which we have here. So go back to the top view. And what I'm going to do now is similar to what we did for the columns, is just copy them all the way across. So first I'll select the inside braces. And I'm going to tell it to copy these a distance of 15 meters 2 times in the X direction. So here we have them in the middle and we have them at the end. And now we're going to copy the outer 2 sets. And for this, it's going to be more often. We're going to have them in each one. So this is going to be every 5 meters in the X direction 6 times. So now we have them all the way around. So our roof is now complete with the bracings, and I can now go back to any section and just tell it to activate all. So the last thing we want to do is create the side braces. And these I'm going to draw on one side of the structure and then just copy them across. So we'll go to create. And this is where it starts to get a little tricky in 3D, since you want to make sure you select the right node to not accidentally connect it to some node that's in the model behind, but you might have a hard time seeing it. So there's things you can do to kind of help you identify this a little easier. For instance, if I go to view, hidden, I can change the view back to just what would be lines and nodes. And that makes it a little easier to identify points of interest. So here I'm going to select the truss element. It's a brace. Again, deactivate this option and just start connecting the first 2 columns on each end. So here I just want to make sure that I selected it indeed only for the front face on this side, and just do the same for this side. But as we saw, I could easily just copy those in any direction. And so I just rotate the model one a little bit just to make sure everything is connected properly. And if I go back to this hidden view, it's a little easier now to identify. So now I'm just going to select both of these and copy them across so I don't have to draw on the other side of the face. So I'll go to translate. I will select only these bracings. And this time it's going to be in the Y direction. And we're going to copy them just one time, 15 meters, since we know that's the width of our structure. So we see now they're also at the other end. If I rotate the model, our structure being pretty symmetrical, these kind of commands make it easy to do these kind of things. So we're done basically with the modeling of the structure itself, and we can start moving on to the other tabs like applying boundary conditions. So we can apply different kind of boundary conditions, and even in this tab there's other things like commands like beam end releases, moment releases, different kinds of links. You can even model the the soil or like the behavior, the interaction with the soil springs. But in this case, we're only gonna fix the bottom of our structure. There'll be other tutorials in the future that get more advanced and start showing some of these other commands. So for this case, we're just gonna all we're gonna define is fix the degrees of freedoms of displacements. We're gonna allow the rotation to happen. I'm gonna do a side view, and I'm just gonna draw a rectangle to select all my bottom nodes and apply it. So now we have the icon that's representing this boundary condition. And so now we can move on to what would be the loads. So we go into the next tab. Before we get started applying loads, what we need to do is define the load cases. So for this particular tutorial, because we're starting off with something very simple, we're only going to have dead loads, live loads, and wind loads. Like I said, this is the first of a series of trainings. So there would be, the upcoming tutorials will look into more advanced types of loading, like other things like what would be the seismic static, or what would be even eventually response spectrum, pushover, time history, all those other kinds of analysis. But just bear with us, and as a starting point, we're starting with something very simple, which will just be wind loads and dead loads and live loads. So we'll have a wind load in the X and in the Y direction. So we have these 4 cases. First thing we'll do is apply the self-weight, and we're just going to group that into the dead load. All we have to do is tell it that it's in the vertical direction and acting in the negative, and here we're adding it to the dead load case, which we can see here in the worktree. As we've been working, everything starts to get organized or grouped here. And now we want to apply what would be called floor loads, but in this case we only have a roof really, so we're only going to apply it to the roof itself. So first we have to define it. So we can just say this is the roof load, and from here we select the case, and then we apply the value. So the dead load in this case, we're going to put at 2 kilonewton meters, but we have to give it a direction for it to make sense. So I'm going to give it a negative so that it's in the down direction. And then I'm going to do live load, and I'll make this 4 kilonewton, but again, negative, so it's going to be acting downward. And I'm at it. So now we've created the case. I can close it, and you can create multiples. If we were having a more complex structure, you can create a floor load type for what would be the, let's say it's a hotel, you can have one for a lobby, you can have another one for what would be a loft or different apartments, you can have another one for what would be maybe stores. So you can create all kinds of floor load types and then apply them separately to your sections or structure. But in this case, it's a very simple tutorial, so we only have one kind, which is the roof. So now we're going to assign it. And we have different distribution methods. This has to do with the diagram. In this case, we're just going to do one way. We're selecting here the floor type roof. Again, there's only one kind for this matter. And we just have to draw a closed boundary, a closed area. We see here, I'm going to do this to both sides of the roof, basically. So I did this to each end, and you can see them now, the representation of this load with those arrows. And I do this, I rotate the model, and I do the same. I just select the 4 corners that encompass basically what would be my floor. So now I've applied the other load to the other side. And now we see that we've created these 2 floor loads, applied them to our structure. So we can move on now to what would be the other kinds, which would be the wind loads. But before we do that, what we want to actually do is generate story data, as we call it. We'll go to structure, building, story data. So we're going to be applying wind loads automatically, but the program needs to identify the location of our nodes, the heights of our key nodes as it's going to be applying that wind load, lateral load, static loads to those directly. So you can just tell the program to generate this information for you to automatically find the location of the heights of your different nodes. And so the program has identified the level, and it's assigned basically floors to each of these locations. And here you can actually decide if you want to modify, if you want to consider the floor diagrams or not. So now that we had auto-generated the story data, then we can go back to load. In this case, we're only working on static loads, like I mentioned. There'll be other tutorials where we'll look at more advanced, like moving loads or dynamic loads or even construction stages. And what we want to do is do the lateral wind loads. We're going to add. So we'll do the first case for X. And again, we have different wind load codes you can select from. And basically they have different, some of them are international. So you would just select from the list which one you want to work with. In our case, we'll be working with UBC. And so you can then, depending on the wind code, there's going to be different parameters to fill in. In this case, using this code, UBC, then you can select the exposure category, assign a basic wind speed, stuff like that. What you want to do is, since we're working in the X, we want to give it a direction of 1 in the X. This is almost like a scale factor, as it says here, and 0 in the Y. And then we want the program to generate the wind profile for us. So here we're looking at the wind profile for the X direction. The program has found the location of these nodes and how much pressure it's going to apply to each. So we just apply this to generate it. And then we select from the menu the Y. And all we have to do is select in the opposite, give it a scale factor of 0 on the X, a scale factor of 1 on the Y. We keep the exposure the same and generate a different load profile since we're in a different direction. So this is for the story force. You can check a look for the story shear, over turning moment. So you can get an idea of these looking here at the profiles. And you can even make like calculation sheets if you want it. So now we have all our loads created. And so what we want to do next is actually do the load to masses. And for that, we would give a scale. So we want to do the one for the dead load, which will have a scale of factor of 1. And then for the live load, we can do scale factor of 0.8. Again, this is just whatever it is that you want it to be. And there they've been generated. And lastly, in structure type, I also want to convert the self-weight into masses. So now our structure, again, a very simple analysis. Our structure is set, our sets of loads, our boundary conditions are all ready. So we can actually now go to analysis and simply perform. Now, depending on the type of analysis you were doing, if you were done, eigenvalue, you would have to set up some other additional conditions, or P delta or seismic. It would all depend. But for our case, the model is ready. So we can go ahead and just perform the analysis. So we see here in the window, we're getting a message. And actually, it took a very short time to run, less than 3 seconds. Again, a very simple analysis. So we can now go to the next tab, which is the results. And we see here we have all the results grouped depending on the type of analysis you were doing. You could select different things like modal shapes or influence lines for moving loads, stuff like that. But for us, we're working on very simple type. So we'll just do, for instance, let's take a look at displacements. And you can select from the load case. For instance, what if we just want to see the displacements for the live load? I want to see them deformed, and I want to activate the legend. If I want to modify the legend, I can click here on these buttons. I don't like exponential view, so I rather have a fixed, let's say 2 decimal points. But it's very small displacement. The deformation is exaggerating, so I have to change my units to millimeters. And now we see that we have about 4 millimeter displacement for this load. If we were to look at something like at the wind load in the Y direction, then it looks a little different. We can also see other results like our forces on the beam diagrams, for instance. So let's say you want to see the moments for this load, or the axial forces for the live load. So you basically select the type of load and the type of result you want to see and click apply. And you would get you can choose the units back to what you want. And this is how you would see for the whole structure. Now, if you want to get a more detailed result inspection of a particular element, then ManagedGen does have that option. So we go here to beam detail analysis, and you have to tell it which beam. So we can just select a particular beam of interest. Let's just say one of the roof beams for the load case, in this case the live load. And you can select the kind of option you want to see. But you can get this kind of detailed graph of what your shear forces are, your bending moment diagrams, your displacements in the different directions for this particular element. So you can get very detailed into some of these sections, or just for the whole structure itself. So we've ran a simple analysis, and now what we can do as well with the program is start looking at the design. So for me, in order to run a design in the program, what I also have to do is create load combination cases. And the program can do this automatically depending on the type of material you're working with or type of design you want to do. We want to, obviously do steel design. So I can just auto-generate this depending on the code that I select. In this case, I'll do the AISC, but we have a list of different international codes you can also work with. So we'll do the LRFD. And the program automatically generates all the load combinations. You can even add additional ones if you want it, and specify or modify the factors for some of these. So you have complete control, but this is auto-generated. But you can additionally add, create your own if you want it. So now that we have the load combinations, we could actually even look at results. We're looking only at 4 cases, but if we were to go back, you can now also see results for these load combinations, depending on which one you wanted to see. And the results would be different, or, they're going to vary depending on the case you choose. Okay, so now we can go to design. The program allows us to design steel, reinforced concrete, just concrete like by rebar, or steel reinforced concrete, or even some of those combinations. In this case, we're working with steel, and this is the code we're using. We're using the same code that we did for the load combination. The first thing that I want to tell the program is actually to give the sections a check based on the code. So the program's working away, and it's going through all my sections, and it's going to give me a report of which sections are good and which sections are not good based on the code. So we see here we have a list, the red being the braces that didn't pass the code. Actually, what I meant to do first was a code check. I think I might have accidentally pressed design, which we are going to get to. So here it's actually first doing the checking. But as we can now expect, some of the braces are not going to pass since we already saw it in the previous. So here we have the results for the code check, and as we mentioned, or we had seen, the columns and the beams are fine, but some of the braces, this is only for the section, but I can actually specify by member. We see some of these are in red and it says not good. I can actually tell them only to show me the ones of interest, which are the non-good ones. And I can actually even tell it, like, to connect it to the model. I'm interested to see which ones are the ones that are not passing. So if I select them, select all, we see them light up in red in the program. And so it turns out that it's the front face braces for the bottom at each end that are having the issue. And we can get a little bit of a graphic report to see exactly what's going on. So here we have the drawing of, the cross section, as well as, which ratio it's filling, the slenderness ratio, the actual strength, and the compression bending. So it tells you which ones it's passing and which ones it's not. So it's fine on the bending strength and shear strength, but it's not for the actual and the ratios. So from here, what you could tell the program, you can actually even get a more detailed report. So now we would go back and tell it that, yes, we want now to do a design, optimal design. Now, this makes more sense in Gen if we were talking something about reinforced concrete, because what it would do is it would design the rebar distribution for you based on a certain section. For steel, it's a little trickier. You would have to specify criteria, or you could specify criteria. You can select a list of sections for the program to consider, and the program would then tell you out of that list which one is the best. If you don't do that, you can just tell the program to give you some options within some general parameters, but it won't be as ideal as, if you had in mind what sections you could choose from. So like I said, for steel, you have to be a little bit more involved directly in which parameters you want the program to consider when it proposes alternative sections for you. When it's concrete, then it's easier, because then you just have to give information about the rebar, and the program will optimize the rebar reinforcement for you. So here the program will notice has come up with a suggestion. It's telling us that it should be thicker. We had originally given this a thickness of 11 millimeters. The program is saying like, well, actually it could be 19 to pass all your requirements. And you can actually even get a small report, graph report of the differences between the previous section and what would be the new section. But we didn't really give the program too much information, so it locked most of the dimensions in place. All it really did was suggest a thicker bracing. And so we could tell it to update it, and then to run the analysis again, and to run the design again. However, what we can also do, if particularly for steel, if we wanted to make it the most optimal section itself, we could send it to our program Design Plus that connects directly to our structure. We can link it, as we call it. So we'll go to Tools, and we'll open this program called Design Plus. And this is almost like a sub-module, a sub-program of this that does the optimal design in terms of not just, if we were talking about concrete, not just rebar design, but even section itself. So here I'm opening the program. I want to start a new file. So I'm going to import sections from Gen, and it's going to import the dimensions, and it's going to import the loads. And then I will design that section, that optimal section, within this program. And it won't only be to pass the norm, but actually I can even give it more specific requirements, for instance, to use the least amount of material while still being strong enough for, to pass the norm. So we see here we can do it for reinforced concrete, all kinds of sections, as well as steel. We're just going to bring in a beam from the roof. So what we want to do is we want to link it first. So this program actually can work independently. You can just specify your own section as we did, apply it specific loads, and run a check or a design. But we can also link it directly to our project. we connect it to the model we were working on. And then now when I select a section, let's just say this top beam here, we see that it's element number 103. It's now connected. The member has been identified and I can now import it. So this top beam 103, the program has imported the section. The program then has the dimensions. It'll calculate all the areas and stuff. It has also imported the loads from this analysis, the moments and the shear forces. So we currently see these dimensions drawn out. I can first tell the program to give it a check based on what we have defined. And we already saw the beams were fine, but maybe there's a more optimal beam section that doesn't use as much material. Well, this is where I can tell it specifically now, design this section for me. And again, we're using the same design code. You can specify whichever design code you want. So now we see that the section has actually been dramatically reduced in dimensions. We're using a lot less steel, but we're still passing all the requirements, the actual capacity, the moment capacity, and the shear capacity. And so you could go back, the program is actually telling you like, you should actually be using a section of 24 by 55. So you could go back to Gen and change the dimensions and run the analysis again in this kind of iteration process to get the optimal. Specifically for steel, you really want to use the least material possible. So this tool is great for that. And then lastly, what you can do other kinds of things. You can get a quantity report, you can get a CAD drawing, all within Design Plus. So that would be the conclusion to this particular tutorial. In this case, in the tutorial, the PDF, we did it for bracing, but we saw that for a column. So I'd like to remind you that we will be posting this in our website. So for the North America.mattersuser.com, you can go to the review courses, and you can see, for instance, we had a training a couple days ago for our GTSNX program. We'll be also uploading here for our building. But thank you very much. That's the conclusion to this tutorial.